There is an experiment in physics that sounds like someone made it up during a very weird lunch. You fire tiny particles at a wall with two slits. If nobody checks which slit they go through, they act like waves, spreading out and making stripes on the screen. But if you try to watch which slit they use, the stripes disappear. Suddenly, the particles behave more like tiny bullets. That is the basic mood of the double-slit experiment. Because from far away, it sounds like reality has one rule when you are not looking and another rule when you are, which is rude. So today, let us ask the dangerous question. What if the double-slit experiment proves reality is watching us? Not literally. There is no tiny security guard yelling at electrons. But the experiment does point at something strange. The universe does not always seem to have one neat story ready before measurement. Start with the simple version. Imagine throwing little marbles at a wall with two openings. Each marble goes through one opening or the other. On the screen behind the wall, you get two clumps. That makes sense. Now imagine water waves hitting two gaps. They spread, overlap, strengthen in some places, and cancel in others. On the far wall, you get stripes. That is called an interference pattern. So far, nothing too cursed. Marbles make clumps. Waves make stripes. Then physics says, now do it with electrons. And electrons say, I will be annoying. If you send many electrons through the two slits without checking their path, you get an interference pattern, stripes. That is wave behavior. But electrons are also detected as individual hits on the screen. One dot, then another dot, then another. At first it looks random. But after many electrons, the dots build up into the same striped pattern that waves make. Each electron arrives like a particle, but the overall pattern acts like it went through both slits as a wave. It is not just a crowd effect either. Even if you send electrons one at a time, the pattern still builds, as if each tiny event is participating in a bigger wave-like possibility. The tempting explanation is the one everyone loves. The electron knows you are not watching, sneaks through both paths, then panics when you install a detector. This is a fantastic story, but it is not quite what physicists mean. The important word is not watching like human eyeballs. The important word is measurement. To know which slit the electron went through, the electron has to interact with something. Maybe a detector, a photon, or an apparatus. The system becomes entangled with the measuring setup and path information leaks into the world. And once that path information exists, the interference pattern disappears. So it is not that the electron is shy. The question, which path, changes the physical situation. That sounds less mystical, but it is still weird. In everyday life, measuring does not usually change the thing so dramatically. If you look at a sandwich, it does not stop being lunch. But quantum systems are delicate. At tiny scales, interaction is not a passive glance. It is part of the event. Trying to learn the path is like walking into a quiet room with a drum set. You only wanted to check what was happening, but now you are part of the noise. That is one reason the experiment feels so creepy. Some facts may not become definite in the familiar way until measurement. This is where people often take a giant leap. They hear observer effect and think consciousness creates reality. That is clickable but much stronger than the experiment proves. A detector can remove the interference pattern without any person watching live. The measuring device only needs to interact in a way that records which path information. So if reality is watching, it is watching with interactions. The universe may not care about your attention, but it cares a lot about information. What counts as information? If the path could be known in principle, even if nobody checks the file, interference can disappear. That phrase, in principle, is where normal intuition goes to sit in the hallway. Because quantum mechanics is not just about what we personally know. It is about whether different possibilities can still combine. If the alternatives remain indistinguishable, they can interfere. If a reliable path record exists, they stop behaving like one combined possibility. It is physics, but it has the emotional flavor of gossip. Once the path information is out there, the particle cannot pretend it was mysterious at the party. Quantum eraser experiments make this even more dramatic. If which path information is available, interference disappears. If that information is erased or made unusable in the right way, Interference-like patterns can be recovered in the correlations. It is not a particle changing its mind because you deleted a file. It is about how outcomes are sorted and what information is available in the full experiment. Still, erase the path information and the pattern comes back is almost too good. It is the kind of sentence that makes physics look guilty, like reality left fingerprints and tried to wipe the table. So what is actually waving? This is one of the deepest questions. In quantum mechanics, we describe the electron with a wave function. The wave function is not a tiny ocean wave. It is more like a mathematical object describing possible outcomes and probabilities. Before measurement, the electron is not simply a little ball secretly taking one ordinary path. The wave function includes both path possibilities. When those possibilities overlap, they can interfere. When measurement gives which path information, that interference is destroyed. Different interpretations of quantum mechanics argue about what this really means. Physics found a working recipe. Then everyone started debating what the recipe says about reality. One interpretation says measurement causes collapse. Many possibilities, one actual result. Another says the wave function never collapses. Outcomes branch into different parts of reality. That is the many worlds flavor. Another focuses on information and relationships between systems. Several serious interpretations exist, and none feel completely normal. Quantum mechanics is extremely successful. It helps explain semiconductors, lasers, chemistry, and the technology in your pocket. The problem is that our imagination was built for chairs, cups, doors, and invoices, not electrons politely refusing to be classical. The double-slit experiment also teaches something humbling about scale. At human size, quantum weirdness is usually hidden. Objects interact constantly with air, light, heat, and the environment, which destroys delicate interference between possibilities. This is called decoherence, and it is one reason your coffee cup does not behave like a wave through two doors. Thank you, decoherence. Very considerate. At tiny scales, if you isolate a system carefully enough, the wave-like behavior becomes visible. Reality did not stop being quantum at our scale. It just became too entangled with everything around it to look mysterious in the same way. The weirdness is not gone. It is buried under constant interaction. This is why the experiment is such a perfect internet topic. It gives you one clean, almost cartoonish mystery. Not watched, stripes, watched, no stripes. Behind that contrast is a serious idea. Reality is not just tiny objects with fixed properties waiting to be discovered. At quantum scales, what happens depends on the whole experimental setup. The question you ask matters. That is stranger than particles are shy, and more interesting. So does the double-slit experiment prove we live in a simulation? No. But you can see why people go there. In video games, distant objects are not always fully rendered until needed. In quantum mechanics, some properties are not classically definite until measurement. Physics is not automatically a computer program just because it feels weird. But as a metaphor, it is fun. The universe sometimes feels less like a warehouse of finished objects and more like a rule system producing outcomes through interactions. That does not prove a programmer. It does make reality feel less solid than it pretends. Here is the funniest part. The double-slit experiment is not rare, hidden knowledge. It is one of the standard doors into quantum physics. Students learn it, textbooks explain it, and labs can demonstrate versions of it. Because the conclusion is not, we understand nothing. It is worse. We understand enough to know reality is not built for our comfort. The experiment works. The predictions work. The technology works. But your mental picture keeps turning electrons into tiny marbles with secret schedules. And electrons keep refusing the roll. So what should we take from this? Not that your mind magically creates the moon. Not that reality is fake. Not that staring at your bills will collapse them into zero. Sadly, the better lesson is that real is stranger than obvious. The everyday world is a stable surface built on deeply non-everyday rules. The double-slit experiment is like a tiny crack in that surface. For a moment, you see the machinery, possibility, measurement, information, interaction. Then the familiar world closes over it again, and your coffee cup remains a coffee cup, probably for the best. Still, it is hard not to feel watched, not by a person or a cosmic eyeball, by the rules themselves. Reality seems to ask, do you want a wave story or a path story? Because you may not get both at the same time. That is the haunting part of the double-slit experiment. It does not say the universe is conscious. It says the universe is picky about what can be known together. And honestly, that may be weirder. So if reality changes when we measure it, what do you think is really doing the watching?